Hello and good morning, CTS265, Section 840 students for the Fall 2016 semester at Anne Arundel Community College. This is the CCNP route course, and this morning's video tutorial is going to be on Discovery Activity number 6, where we're going to again continue the conversation on EIGRP, and we're going to be taking a look at EIGRP from a load balancing perspective. And so again, we've got another fantastic Cisco Learning Labs activity here that has everything set up for us and ready to go. And let's take a look here on the HQ router. They are asking us to confirm that we've got reachability to the segment over behind the branch router, and so that would be the 192.168.0.1. And as you can see, we do have reachability. Now, the next thing we want to look at is the routing table. So if we were to say show IP route EIGRP, you can see that what we have right now are two equal cost paths over to the 192.168.0.0/24 network. However, and actually let me get the utility up here, and we didn't want that one right away. We want to look at the diagram first. As you can see, we have three pathways over to the 192.168.0.0/24. And so these are both 4 megabit per second WAN links here. And then we have a 1 meg connection coming down this path. And so we're simply going to say WAN 1, WAN 2, and WAN 3. So we've got three options, but in that HQ routing table, we're only seeing the two equal cost paths. Well, let's take a look at the EIGRP topology table. Why do we not see that third table, or it's a third table, that third path? So show IP EIGRP topology, and what do we see here? So let's pause and let's talk about some of these values, because this is going to become very, very important. And this is what we were stressing on Monday night when we see the output in the show IP EIGRP topology table. You can see that we have the feasible distance value, right? And it's clearly marked FD is 409,600. Now, we also see that same value as the first value in the parenthesized values here. However, that is not the feasible distance. That is the computed distance. Right? And I told you that some of you were kind of gave me an odd look and were like, well, no, wait a second, that is still the feasible distance. But no, that is actually the computed distance. Now, remember, the feasible distance value for the specific successor route is the feasible distance value, and it's set from the last time that that successor route transitioned from the active state, make sure active, I spelled that wrong there, active state to the passive state, right? And the passive state being represented with the letter P, and active state would be a letter A, and active is bad because that means that the topology is converging. Passive is good in that the topology for that successor route is fully converged. So that is when the feasible distance value is set, and it will stay set until that successor route transitions from passive back to active. Then, and I keep spelling active wrong, and that's terrible there. Then it will be recalculated, because when it goes active, the topology for that successor route is reconverging. However, these values here, the computed distance, those values can actually change. And as long as they change in a subtle fashion, subtle enough so that they don't force the successor route into the active state, you will see the computed distance values can actually change, and they change on the fly. This is not the feasible distance. That is the computed distance. Okay, and so the first value in the parentheses, I think is how you might say that, but in the parentheses here, the first value that you see is the computed distance. Then we have the slash, the forward slash. Then we have the reported distance, right? And remember, the reported distance is the distance being reported by the successor, right? So the successor is reporting the reported distance, which is the next hop, I shouldn't say the next hop route. Well, I guess it is the next hop router's view, or the next hop router's cost metric, composite metric, their cost to get to that successor route. That is the reported distance. And so the feasible distance is nothing more than this router's view going through each of these three successor routers, right? It's that cost to get from the HQ router to the successor, to the next hop router, plus their reported distance. And that gives us the feasible distance. And if anything changes during that time that doesn't force that successor route into the active state, it's the computed distance that we will see change. And so those are the important values. Now, in the show IP EIGRP topology table output, remember that if I don't use the option all links, what am I seeing? I'm only seeing the successors and the feasible successors in the show IP EIGRP topology output. If we had a non-feasible successor, right, that would be, we would have to use the all links command to see that. Because again, show IP EIGRP topology only shows me successors, of which there could be one or more, and feasible successors. And remember, in order to be a feasible successor, that successor path, that router, that next hop router, must meet the feasibility condition if they are to be a feasible successor. And so then that leads us to the next logical step. Well, then what is the feasibility condition and how does a successor meet that? A successor meets the feasibility condition if and only if their reported distance is strictly less than and actually I should probably draw it this way, is strictly less than the feasible distance of the current successors, or I should say successor or successors. And so let's clear the screen here and talk about the feasibility condition specifically. So here is the reported distance for each of the three successors, right? Now, whether they're feasible successors or not is going to be dictated on if this reported distance is strictly less than the feasible distance of the current successor. If this condition is true, then you are a feasible successor. Now, keep in mind, we have two equal cost successors here, right? So we will be doing equal cost multipathing over those two successors. And you can see it tells us we have two successors, which means we have two equal cost paths to the successor route. But then we have this third one that we're not doing equal cost multipathing over, but this guy right here, or gal, qualifies as a feasible successor because their reported distance is less than the feasible distance of the current successor. And it must be less than. It cannot be less than or equal to, because the dual diffusing update algorithm, right, which is what is performing the computations for EIGRP, states that mathematically it can provide loop freedom, guaranteed loop freedom mathematically, because What we're saying is if your reported distance to get to that successor route is strictly less than my feasible distance to get there, it is mathematically impossible that you would be looping through me, the HQ router, in order to get there. That's mathematically not possible, and that is how the loop freedom is guaranteed, right? Remember, strictly less than, not less than or equal to. It's got to be less than. So these prefixes, or I should say these successors, and that's our feasible successor here. Remember, successors are listed first and then feasible successors later. This qualifies as a feasible successor. If the reported distance did not qualify, it would not show up in this output. And so let's do this. Let me show you what would happen and how do we manipulate it. When we're looking at it from the perspective of the HQ router, it is looking at the outgoing interface values, right? The cumulative delay and the slowest bandwidth speed. And we know that we don't want to manipulate the bandwidth because it could affect quality of service settings, and more importantly, what if other routing protocols are running across these links? It could have a serious effect on those other routing protocols as well. And so if we were to manipulate the value of the delay for this prefix and it were to show up here at HQ and it was so bad that it didn't qualify as a feasible successor, it would disappear from that table. So let's come onto the branch router and let's go into global config and say do show IP interface brief. And we can see we have all these interfaces here, and we're most interested in this one here, serial 20, because that is WAN link 3. And where is serial 10 there? Hold on one second here. Oh, Ethernet 0001. Sorry. So it is serial. I thought these were all serials. My apologies. So we'll come back to the branch router here, and we're going to go into interface serial 20. And if I were to say delay, and I do a question mark, you can see it's in tens of microseconds. So I'm going to put in here 1, 2, 3, 4, 5, 6, 7. Right? We're increasing the delay substantially, but we're doing it on the branch router. So now if I come over to HQ and I say show IP EIGRP topology, what happened? Right, nothing happened, right? From the perspective of EIGRP, from the HQ router's perspective, it's looking at the outgoing interfaces. And so we'll recall, let's recall this command and we'll say no. But if I come to the HQ router, and let's make sure we get the right interface, serial 10, and I go into global config, interface serial 10, from the HQ router's perspective, if I say delay 1, 2, 3, 4, 5, 6, and let's see if that's enough to do it, and then we say do show IP EIGRP topo, did anything happen there? Yeah, take a look. Right? You can clearly see that the computed distance increased substantially. But did anything happen here? No, the reported distance is still the same. So again, the reason I'm going through each of these is to drive home the point here of when we're talking about manipulating the EIGRP metrics. I manipulated it here, and from the perspective of HQ, that had zero effect, right? So there was no effect. I manipulated it here, right? But again, it didn't manipulate the reported distance because the reported distance is a value that is being reported from this branch router. And so that would be the outgoing interface from the perspective of the branch router that would then report out a much larger delay because, again, remember, it's from the perspective of outgoing interfaces when we're saying the cumulative delay. So manipulating it here isn't helping the reported distance be tweaked with the HQ. Doing it here, it's not going to work. It's got to be there because the reported distance is a value the branch router is reporting, but again, it's based on the cumulative delay in the outgoing interface direction. So let's come back to the branch router and let's see what happens if I go into loopback 0 and say delay 3, 4, 5, 6, and we'll put a 7th one in there. Now when I come over to the HQ router and say do show IP EIGRP topology, take a look at what happened. Yeah, it manipulated the delay, but it did it for whom? It did it for everybody, and did it force it into the active state? Absolutely, it tweaked it just enough to force it to go passive, because if I say do show IP route, it's only been in there for 26 seconds with that computed distance. And so again, remember, to impact that reported distance, we're doing it from the successor, and remember, successor equals router, from the successor who is reporting those values, right? And in this case, it's that branch router, and it reports it across the board. But again, we did it with such a big value here, we wanted to force that into the active state. Okay, so let me pull that value off of there because that is going to cause later issues. And would that force it into the active state again? And it absolutely did, because you can tell the feasible distance has changed. Show IP route, EIGRP, or show IP route, it's only been in there 13 seconds, so it went active and then went passive again. Okay, so now let's talk about load balancing, right? So we know that we're going to be able to do equal cost multipathing based off of what we see right here. We have two successors that have equal costs to get to this successor route. So the variance command. Remember, the variance command has nothing to do with the maximum number of paths, and I'm going to manipulate the max paths value as well. But max paths by default, if I say do show IP protocols, max paths by default on this platform is 4. Now, we can probably tweak that up to 32. I think on most platforms, most iOS or ISR platforms, we can get up to 32. In fact, if I were to take a look on one of my, and that's a 2811 router, so if I were to say, go into global config router, EIGRP1, and then say max paths question mark, yeah, we can go from 1 to 32 on that platform. Here's a 2610, a much older router. Let's go into global config and say router EIGRP1, and if I were to say max paths on this platform, take a look. So the older platforms, there is a difference. In fact, newer platforms, it could scale, who knows, on the Nexus platform or on the ASR. You may, who knows, I don't know. I would have to take a look. In fact, I do have some ASRs and some Nexus boxes I can look at, so I probably should have taken a look at that. But it may be greater than 32. Maybe it's 64, maybe it's 128 or 256, who knows. But again, remember, it will be platform dependent. This is 2610, we can only do 16. On a 2811, I can only do, or I can do up to 32, so double what you could do with the 2610. So keep that in mind. But again, variance has nothing to do with max paths. And what I'm trying to say there is, by me manipulating the variance value, I am not manipulating the maximum paths value. Max paths is going to be, you can see it's 4. It's going to be 4 whether I make the variance 5 or whether I make the variance 128, right? The default variance value is 1. And so what this exercise is all about, it's all about performing unequal cost multipathing. Because again, if I say do show IP EIGRP topology, you can see how many possible successors could I load balance across. Exactly, I could do it across 3. However, now we need to talk about the requirements for unequal cost multipathing. And the first requirement to guarantee loop freedom is that it must be a feasible successor. So in order for me to take a path and to do unequal cost multipathing across that path, it must meet the feasibility condition. And so this is why I stress these values and these terms in all of the EIGRP videos where we're talking about multipathing, right, or load balance or load sharing, is because in order to understand the variance concept and the variance values that you're going to use, you have to understand the feasibility condition. And again, that feasibility condition states that in order for me to be a feasible successor, I must meet the feasibility condition in which my reported distance must be strictly less than the feasible distance of the current successor. And so when we're talking about unequal cost multipathing, I can only use successors and feasible successors when I'm doing that. So I have to understand the feasibility condition. And that's one of the other important reasons that the show IP EIGRP topology command by itself only shows successors and feasible successors, because this command right here gives me the output required to say, could I use that third path? Well, I can, and I know that I can, because if I couldn't use it, meaning it wasn't a feasible successor, it wouldn't show up in this output. Because again, show IP EIGRP topology only gives me successors and feasible successors. And that is the number one requirement when we're doing unequal cost multipathing, or I should say the number one requirement that needs to be met is in order to use another successor for unequal cost multipathing, that successor has to be a feasible successor. And again, it could be, we could have 20 feasible successors here, but the bottom line is to do unequal cost multipathing across a path that is not a successor, it has to be a feasible successor. So when someone asks you, hey, could we do unequal cost multipathing across those 7 paths? If any of the 6 other paths, in addition to the, we'll say there's 1 successor, across any of those paths, they all have to be feasible successors. Or else the conversation about unequal cost multipathing across those successors stops right there. However, here in our scenario, the conversation will then continue because we can conclusively say that all 3 of these paths meet the feasibility condition. And so obviously we have our successors, but we have our feasible successors. So condition 1 for unequal cost multipathing using the variance command continues. And now we continue to the second part of, or the second requirement, and that is that the cost, or I shouldn't say the cost, the computed distance, which again is not the same as the feasible distance in this case here. The computed distance for the feasible successor needs to be strictly less than the feasible distance or the computed distance of the current successor, right? So how could we figure that value out? Well, and there's a couple ways you can look at it. You can do division, and you can divide the computed distance of the feasible successor by the computed distance of the current successor, and that's going to give us a value. So let's do it by division first. Okay, there we go. So I had forgotten I had tweaked the delay here, which blew this value up to a artificially super high value. So again, we there's two ways that we can come up with the variance value, what value it is we're going to need in order to include this third successor in unequal cost multipathing. So the feasibility condition is met. It is a feasible successor. So if it's a feasible successor, then we can include it in unequal cost multipathing. And all we need to do to get that value, and I will pull the calculator up here, is to simply divide the computed distance of the feasible successor by the computed distance of the current successor. And then that's going to tell me what the variance value would need to be. So we're going to take 229,7856, and we're going to divide that by 409,600, 409,600. And that gives me 5.61. Well, remember, EIGRP doesn't do decimal math. It does integer math, right? So we need to round up. And when we round up, if I say clear, if I were to multiply 409,600 times 6, it gives me 2,457,600. And so the question is, when I put that artificial value, variance 6, in there, what that stands for is I'm saying that any feasible successor, right? Because remember, in order to use the variance equation or the variance multiplier on a possible path for unequal cost multipathing, what I'm saying is I'm going to artificially say that if there is a feasible successor who has a computed distance that is less than the computed distance of the current successor, so the computed distance of the current successor times the variance multiplier, then they can participate in unequal cost multipathing. And I know that's a mouthful. So to break it down, what we're saying is if that value is less than the computed distance of the current successor times the variance multiplier, then this can participate in unequal cost multipathing. So I showed you that my preferred way is to simply do that, is to take that number and divide it by the computed distance of the current successor. And that gives you, typically you're going to get a decimal value, but then you just round up. And so that's very, very simple. The other way to do it would be to sit here and, try to guess, right? And say, okay, so 409,600 times, and if I look at it, times 5, is that less than that value? No. Okay, let me multiply it by 6. Is that so? Again, to get the definitive answer, simply divide the computed distance of the feasible successor that you want to use by the computed distance of the current feasible successor. We got 5.61. We simply round that up to the next whole number, 6, and now we know the value that we need to use in order to include that third successor who is a feasible successor in the unequal cost multipathing. So if I say show IP route, you can see we've got the two equal cost paths. So now what we're going to do is we're going to tweak that variable on the HQ router. We're going to go into global config. I'm going to say router EIGRP1, where we say variance, and again, it's between 1 and 128, and I say variance 6. So what we saw before I had realized that I had left the delay, I think it was 999999 command on the interface, is that if we would have done the division then, it would have been like 629 point something something something, and no. EIGRP is smart enough to say, yeah, no, you're crazy to try to do that. We are not going to use that path. Because again, I can only go up to 128 times the computed distance of the current successor. If it was 129 times that value, then EIGRP is going to say, no, you'd be nuts to do that and use that path. So I'm not going to let you use that path. So now when I say variance 6, do show IP route, There you go. We've got that third path has now been included, and we can actually use that path. But does that change, do show IP protocols, my max path setting? No, it doesn't. The maximum paths is still 4, right? Max paths is still 4, and here you see the max metric variance is at 6, but max paths is still 4. If I were to say maximum paths 3, what do you think we would see in the do show IP route? How many successors are we going to see in there? Exactly, we see 3. But what if I said max paths 2? Then what happens? Exactly. I can only use 2 paths to do my multipathing, right? And there they are. What if I said max paths 1? What's going to happen? It drops it down to 1. And in this instance, if I were to say max paths, if I do the question mark, you can see on this platform, it's IOU, iOS on Unix, I can do 32. But just because I change it to 32 doesn't mean I miraculously now have 32 different paths. Again, there's only 3 physical paths, 3 physical successors which I can go through. Excuse me. If there were 32, then they would all show up here, but there's only 3, so we get the 3. But again, changing the variance doesn't change the maximum paths value, right? Doesn't change the maximum paths value. It simply allows me to do the variance command to do unequal cost multipathing over these different paths. Now, there's 2 things, or there's actually one more thing we need to talk about, and that is the proportionality or the ratio of the traffic and how it's being shared across those paths. Because just because I'm doing unequal cost multipathing, it doesn't mean that one packet goes there, one packet goes there, one packet goes there, and then it just doesn't round robin like this. That is not what is happening. It's because, again, that would be, what is that called? Exactly. That is equal cost multipathing. We are doing unequal cost multipathing. Therefore, the question remains, well, how unequal is the multipathing, right? How unequal is the ratio in which you're doing this multipathing? And it's, again, it's very, very straightforward. And so when we look at the different values that we have here, right, and we're trying to determine what the ratio would be, right? So how many packets are going to go across each of these links? What we would see is the way you do it, and we're going to list them out here, so that we have the first successor, the second successor, and the third successor. So the first successor has a computed distance of 409,600. The second one, the same thing, 409,600. And then we've got this large value here, 2,297,000, is that right? 856. And so in order to determine what the ratio is, we take the largest value and then divide the smaller values into the largest value. And again, we don't use decimal numbers, right? We're going to use whole numbers. And we've already done the division because we know the variance value worked out to be 6. The equation itself produced 5.61 when I divided 2.297856 million by 409,600. But we round that up, and so in order to figure out how many packets would go across per for each link, it would be a ratio of 6 to 6 to 1. So for every 6 packets that go across the first 2 links, we're only sending a single packet, and that is the load sharing ratio right there. So 6 packets go here, 6 packets go here. So for 6 packets that go across each of these 2 links here, only a single packet would get sent across that third link. Or if we're doing, that's packet-based load sharing. If we're doing flow-based load sharing, then it's 6 flows here, 6 flows here, and then only a single flow there. Because again, EIGRP is smart enough to recognize that even though we're allowing this to do multipathing, this feasible successor here, he's part of the multipathing equation, right? It is still not as good a path as these first 2 successors. And so we end up with that ratio of traffic that gets sent across those links. All right. Well, this is going to wrap up our discussion of load balancing with EIGRP, and specifically, we took a good look at unequal cost multipathing or unequal cost load balancing. And remember, the two conditions that need to be met to do unequal cost load balancing. The first is that the path that you're going to be using to include in that load balancing must be a feasible successor. So you cannot use paths that are not through feasible successors in unequal cost load balancing. So again, if you looked at it and you said, wait, that's not a feasible successor, your conversation about unequal cost multipathing stops right there. You can't use that path. Has to be a feasible successor. Secondly, you would need to make sure that the variance value that you're using, that the computed distance of the current successor, when multiplied by that variance multiplier, is strictly greater than the computed distance of the feasible successor that you want to use. And we saw in our case that that value turned out to be 6. All right, thanks so much for watching, and I will see you guys on Monday.